All right, so we're going to get started. Let me go close. Can you go close that door? Sorry, I should have closed it on my way in. Okay, so we're looking at series circuits, and I just wanted to go over series circuits and a little bit about what we talked about last time. We talked about the impedance of series circuits, and particularly with impedance, we have. Let me open up a few toolbars here. Should have a format bar. Good, here we go. So we're going to look at series RC circuits. Can everybody read that? Okay, good. And we already talked briefly about some of this stuff last time, but I wanted to go over that in a AC circuit. Now we're switched over to AC, and we're going to be talking exclusively about AC for the remainder of the semester. We have a series resistor and a series capacitor in an AC circuit. And we talked about how that introduces some unusual behavior. Remember that in a pure AC circuit, in a purely capacitive circuit, in other words, a circuit that only has a capacitor, that circuit will shift the current and the voltage out of phase with each other by 90 degrees. Recall, probably from your first semester of circuit analysis, the Eli, the Iceman. That simple phrase, if you will. And what that was supposed to show you is that for an inductor, voltage leads the current. Right? Voltage leads current, and then the other type, we have current leads voltage. All right? In other words, I comes before E. Right? That's the way it works. All right? So current leads the voltage, or you can say voltage lags the current. You can say it either way. They both mean the same thing. And so what we said was that voltage is knocked out of phase with current by 90 degrees. And that was a product of the fact that the voltage is determined based on the change in current, how fast the current is changing. So when the current doesn't change very quickly, which occurs at the peaks, negative and positive peaks, with voltage is minimum at that point. And so that's what we talked about last time. We also talked about how to write impedance. And so there's two parts to impedance. Impedance is a complex number. The first part of impedance is R, and the second part of impedance is reactance. Specifically, capacitive reactance. And so that's your formula, or your basic format for a series RC circuit. We label x of c as negative j x of c. Those are the same. So R plus negative jx of c. Okay, that's how we write that. That is what impedance is equal to. It's a complex number consisting of a real number, which is the resistance, and a reactance. An imaginary number, which is the reactance. Questions about any of that? All right. As far as good. And if we wrote this as an angle, let's see, write that as an angle. Let's write it. I should have chose the graph paper on this. They do have graph paper. If we write it as an angle, remember that this is 0 degrees here. Here is 90 degrees. Down here is negative 90 degrees. And so the resistance, which I'm going to indicate in red here, let me choose a slightly thicker pen here. Let's do a fine point. Is that a thicker pen? No, it's not really thicker. Let's keep going. Maybe a medium point pen then. I'm going to use this. That's a little bit better. Here's my resistance. That shows up as a vector along the real axis. Alright. And here is my reactance. That shows up as a vector along the imaginary axis. And what we're looking at when we look at impedance is we're just looking at, well, let me label that here. What we're looking at when we're looking at impedance, we're looking at the vector that when we add R plus X of C, the vector we get is the impedance. Or if you want to think of it in terms of triangles, resistance and capacitive reactance form a right angle, and then the hypotenuse that connects those two becomes the impedance. The impedance associated with an angle. So there'll be an angle of impedance. That angle will be between somewhere 0 degrees and negative 90 degrees. It'll be your range. Any questions about that? So your angle theta will be anywhere between 0 and 90 degrees. Impedance will be exactly 90 degrees when the only resistance is the capacitance, the capacitive reactance. And Z will be equal to R when there's only a resistance in the circuit, or when inductance cancels each other out. We haven't talked about this yet, but if we were to have an inductive part of the circuit, the inductance pushes that way. Inductive reactance. So it's possible, and it does happen, at resonance, inductive reactance and capacitive reactance are equal, which means they cancel each other out. So it can happen. Right now we're only looking at capacitance and resistance. And until we do look at that, for now, just consider that all angles are going to be between 0 and 90 degrees. And thus all the impedance vectors will be between 0 and negative 90 degrees. You'll always see they'll be occupying quadrant 4. Okay. All right. So let's we did a couple of examples last time. We can do another one real quick just to make sure we're all on the same page here. So if I have a setup like this, it's hard to look at that. It's kind of crooked. That's all right. We'll get over it. All right, so there's the resistor. There's the capacitor. I'm going to not give the capacitance, though. I'm just going to go ahead and tell you that there's 100 ohms of capacitive reactance and 56 ohms of resistance. So what is Z? What's Z going to be equal to here? The formula for calculating Z is very simple. You can simply write it in rectangular form if you'd like. To do that is very simple. You just take the real part, which is 56, and then you add the non-real part. 100 ohms of X of C is negative J 100. I'm going to set that, and then of course followed up by ohms. So it's 56 minus J 100 is the ohms. That's exactly how we write that. 56 minus J 100 ohms. So that's one way to write it, but it's not usually the way. Normally we write impedance in polar form. It's almost always done that way. So to figure out what it is in polar form, simply take the square root of r squared plus j squared. Now, it's negative, but it doesn't matter. Because when you take something that's negative and square it, it becomes positive. So there it is. All right. So, and what is that answer? Well, you can bring up a calculator to figure that out. Let me do that. Okay. Here we go. And I'll just take 56 and square it and add 100 and square it. And then to get the answer. So I get 13,131, and then what I need to do is take the square root of that. Done. So overall, it's 114 ohms. 114 ohms. Did I get anything different? It's making sense? Well, I think it's 114.6, so I guess if you want to be exact, it might be 115 ohms, yeah. If we round, it's 115. It's actually what the book gets. Questions? So far, so good? So that's the answer there. Now we just need to find the angle. To figure out the angle, remember that we take the negative arc tangent of the capacitive reactance, which is 100, over the resistance, which is 56. So that solution will be the angle that you need to get it in polar form. Again, for the calculator, it's very simple, and you can use the Windows one if you'd like. I wonder if I can make this bigger. Can I make that bigger? Well, maybe not. I'm not going to worry about it. But so to do this computation, the easiest way to do it in the calculator is take 100 divided by 56. Do the parentheses first. You have to follow the order of operation when you use the Windows calculator. So it's 100 divided by 56 gives us that. I need to take the arc tangent of that. Now on here, I don't know where the arc tangent is. Oh, here we go. Inverse. There we go. There's arc tangent. So I click that arc tangent. It gives me 60 degrees, and now it's negative arc tangent, so I just need to throw a negative on there. I can do that by doing that. There it is. Negative 60.7 degrees. Well, 0.75, so I round it up to 60.8. So it's negative 60.8 degrees. Alright, so that's how we figure that out. So if I ask you for impedance, normally I'm looking for, unless I specify otherwise, I'm looking for the polar form of that. So how do we write the overall impedance? I haven't written that yet. Write it like this. It'll be 115 negative 60.8 degrees ohms. Good? Impedance is measured in ohms, and so is reactance and resistance. All of that's ohms. Questions? Let's scroll down a bit. All right. I think I briefly talked about Ohm's Law too. Remember that in these types of circuits, Ohm's Law still applies. So we have V is equal to IZ. Okay, instead of V is equal to IR in AC circuits, V is equal to IZ. We take the impedance, multiply it by the current, we should get the voltage. And you can, of course, rearrange this in a variety of ways. If I know what V and I is, I can determine what Z is. Just rearrange it and solve it. Or if I know what V and Z is, I can find I. So that does all work. Those are all valid statements. Just remember that I'm doing complex addition and complex multiplication. Well, not addition. I'm doing complex multiplication when I do this. Okay? Now, because I'm just doing complex multiplication and division, it's best to keep everything in polar form if you can. Polar form does really well, right, with multiplication and division. So I would leave all that stuff in polar form. unless absolutely necessary. So let's think about how we might apply this. I didn't do this example last time, but we can do it today. Here's an example of a circuit. It's AC, of course. It's got a resistor. It's got a capacitor. All right. So it's a single resistor, single capacitor. Now the resistor is 2.2K, and the capacitor is 0.022 microfarads. All right. Now it tells you that the voltage source is 10 volts at 0 degrees. Notice that it gave you the voltage in polar form. That's key there. And also, the frequency is equal to 1.5 kilohertz. Why frequency? Well, because I didn't give you the capacitive reactance. And if you don't know what the capacitive reactance is, but you know what the capacitance is, which is usually the case, then you can compute the capacitive reactance using the formula. Now, the formula for capacitive reactance, it's a good one to have memorized by now, but if you don't have it memorized, it's X of C is equal to 1 over 2 times pi times the frequency times capacitance. So, of course, the reactance in a circuit is dependent upon the capacitive, or the capacitance of the capacitor, and the frequency. All right. So whatever frequency we have, that's why AC voltages always give you the frequency, is so that you can do that calculation if you need to. So let me go ahead and compute what the reactance is for this particular example. Ooh, that's messy, isn't it? All right, so we got 22 microfarads. All right, so, and 1.5 kilohertz. I'm going to do the denominator first. So I'm going to do, let's see, 0.000. So it's 0.22 microfarads. I'm sorry, it's 0.022 microfarads, so that makes it 22 nanofarads. So there we go. I think that's the equivalent. And I'm going to take that and multiply it by 1500 for the frequency. I'm going to multiply it by 2 and then by pi, and that should handle the denominator. There we are. And then find the inverse of that. And I get 4822, or rounded up 4823, or 4.823. 4.823 kiloohms. That's how much reactance we have. Questions about that? So far, so good? All right. So now we can compute what the impedance is. And what it's actually asking us to figure out is what the current is. In order to do that, then of course we have to know what the impedance is, because we're going to take voltage and divide it by the impedance to find current. So what is the impedance? Well, let's find out what that is. So x of let's see, Z is equal to square root of 2200 squared, right? That's the resistance, plus 4823 squared. We can definitely do that on the calculator, because I do not want to do that by hand. There's calculator. Let's see, 2200. Oop. Square that, and then take 4823 and square that, and then get the result. There's the result. I'm going to take the result and take the square root of that. I get 5301. 5301. And that is the total impedance. That's only part of it, though, right? I need to know the angle. Alright, so again, we're going to find the negative arctangent being the inverse tangent. You'll need to hit, it's normally a second function on your calculator, so you'll need to hit the shift key to access that. It should be right above your tangent function. So if you're trying to find that, And again, we need to take, for arctangent to work, we take the reactance first, 4823, put that in the numerator, and then the denominator has the resistance, 2200. Or, if you will, it's the two legs of the triangle. All right. Let's figure out what that is. Okay, let me type that in first. All right. So I got 4823, and I'm going to divide that by 2200. All right, and so that's just a fraction. Now I got to take the actual arctangent. I hit the inverse here. It gives me my inverse keys. I've got inverse tangent there. And that tells me it's 65. Of course, I have to make it negative. So 65.48 or 65.5 degrees negative. There it is. So overall, we say the impedance is equal to 5.30 kiloohms. Oop, not kiloohms. We got to wait to write kiloohms. 5.30 negative 65.5 degrees kiloohms. Questions about that? Right. There is the result. That's only the first part. I need to actually find the current. So in order to find a current, we of course use our Ohm's Law, the version that works with our circuit anyway. V divided by Z is equal to I. V is given to us. It's 10 volts, 0 degrees. 10, 0 volts. I'm going to take that and divide it by 5.3 at negative 65 degrees kiloohms. All right. So let me compute that real quick. So all I got to do is take 10 and divide it by 5300. .001886. I'm going to round that up though. 0.001887. Yeah, round it up. That's the current. I need to find the angle of the current. What is the angle? It's 0 minus 65. Well, sorry, 0 minus 65, right? We're dividing the angle, so we subtract the angle. 0 minus 65, which means plus 65. So you're right about that. 65 degrees. Positive. Right? And this is in amps. We, of course, can convert it to milliamps by sliding the decimal point over a few spaces. 1, 2, 3. So it's 1.8. I'm going to round up 9. At 65 degrees milliamps. Positive angles means leading. So if the voltage is at 0 degrees, then the current has to be leading by a certain amount. In this case, it tells you it's leading by 65 degrees. Questions about that? That's actually the answer right here. That's the answer. Because that's what asked you to find is the current. Now, current in this type of circuit has to be specified with an angle. Questions about any of that? All right. We're going to keep working our way through. I'm going to show you the RC lag circuit. Call it an RC lag circuit. RC lag circuit. Now, an RC lag circuit is designed to make the output voltage lag behind the input voltage. So you put a voltage in, AC of course, because we're talking about AC circuits. You put a voltage in, you get a phase-shifted version of the voltage on the output. That's what it is. Okay, that's all an RC lag circuit is. Let me show you how to design one. Very straightforward. There's your resistor. Here's your capacitor. And all you do to set up a lead lag circuit is you take the output voltage as measured from across the capacitor. That's all it is. That gives you an RC lag circuit because the output voltage is going to lag because of that capacitor. Okay? So we apply a voltage in, we get a voltage out that's different. To figure out what the difference in angle is, we use a simple formula. It's similar to the one we just did, except it's sort of inverted. This is the Greek letter phi, or phi, or fofum. No, I'm joking. I usually pronounce it phi, but I think I've heard it pronounced phi before. But I call it phi. So there it is. There's phi. It's a Greek letter. Because we can't always use theta for angles. You got to switch it up every now and then. So that's to compute what the angle difference is. So I told you it throws the output off out of phase. To get the difference between the input angle and the output angle, you use this formula. Phi is equal to negative arctangent of r divided by x of c. That's how you figure out what the phase difference is between an incoming voltage and the output voltage. Excuse me. Let's put some values then on this thing. If I have a resistor that's 15K and a capacitor that's producing 5 kilo ohms of impedance or of reactance, then what's going to be what's the phase difference going to be? What's going to be the difference between the input and output in terms of phase? How much in degrees am I going to be offset on the output? Well, again, we use our formula up here. It's very simple. We say that phi is equal to the arctangent, in this case, of r, which is 15K, over 5K, because that's x of c. And of course that means it's the arctangent of 3, because 15K divided by 5K is 3. So what is the arctangent of 3? Well, plug in 3 and take the arctangent of it. There it is. And don't forget, excuse me, this is the negative arctangent. So negative, what does it say? Negative 71.6 degrees. All right. That's how much it's lagging, rather. Questions? Okay. Let's take a look then at another problem. Let's use another circuit here. This is R. It's 680 ohms. And this is a 0.1 microfarad capacitor. And let's figure out what the output phase shift is going to be. And you need to know one bit of other information here. You need to know that this is a 1 kilohertz sine wave being produced by the AC source. Okay? So now you should be able to figure out what the phase difference is going to be. Notice that the output again is taken across the capacitor. That's how you get the lead. That's how you get the lag part. In order to get a lead circuit, you have to switch the positions of the capacitor and resistor. All right. So tell me. Excuse me. What phi is going to be here? First things first, though, you got to figure out what x of c is. 1 over 2 times pi times 1000 for the 1000 kilohertz frequency times 0.00000001 for the capacitor. All right. So that's 2 times pi times 1000 times 0.000001, and then find the inverse. 1591, or if I round up, 1592. Wish people stop texting me in middle class. Sorry about all those dings. Okay, so it's 1592 ohms. Now the next thing to do is to use this in our angle calculation here. So I'm going to take R, which is 680, divide it by 1592. What does that give us? Well, let's see. 680 divided by 1592. Let's find the arctangent, and then it's negative. So it's negative 23.1 degrees. Alright, so it shifts it out of phase by 23 degrees in the negative direction. Alright, which means voltage lags. It's a lag circuit. Questions or concerns? Alright. So I kind of already gave you a hint, but if you want to create an RC lead circuit, it's very simple. You want to take the same circuit and find its output across the resistance. So here's an example of a circuit. There's the capacitor. There's the resistor. If I instead take the output voltage to be across the resistor, then I've created an RC lead circuit. All right. And so an RC lead circuit is fairly straightforward. It's not very difficult. If you want to calculate the phase angle Phi is a little bit different for a lead circuit. You take the arctangent, positive arctangent of x of c over r, and that'll give you your lead circuit, or your phase difference in a lead circuit. Okay, so let's assume that this has a capacitive reactance of 150 ohms. Let's say this resistance has a resistance of 220. Then we should be able to figure out what the angle is. Right, find the arctangent of 150 over 220. Mm, 34.3 degrees. Questions about that? So that's how you do an RC lead circuit. Find the phase difference between the input and the output. Another thing you may have to eventually do for both of these is figure out what the voltage is across them. So I would think it'd be obvious what the voltage is. There's a slight variation if you want to know what the exact voltage value is. You need to be able to, in order to find voltage, you need to be able to compute using basically what amounts to the voltage divider formula. What is the voltage divider formula? R over RT, right? R being the whatever you want to find the voltage across, divided by total resistance in a circuit. What you really want to do is find either X of C or R of the thing you want to find the voltage across, and then divide it by Z in the entire circuit. Does that make sense? Okay. So RT is really ZT in a AC circuit. Okay. All right. So let's say I want to find out what the voltage is on a lead circuit. It's very simple. I just take R and divide it by R squared plus X of C squared. Basically, divide it by Z, right? And then multiply that by the Vn, how much voltage is going in. Alright, so in this circuit, we can assume that let's assume that the incoming voltage was 10 volts. We can figure out what the output voltage is by using a resistor value, 220, dividing it by the impedance formula, which is 220 squared plus 150 squared. Take the square root of that. That gives you the part there in parentheses, and then you just multiply that by 10. Let's see if I can do that. Alright, start with 220. Oh, actually, let's start with 220 squared plus 150 squared. Alright, and then I'm going to take the square root of that. Alright, it's 150. And then multiply that by 10. Oh, hold on a second. 220 squared plus 150 squared. Alright, let's try that. I think I got a different answer that time. Oh, so I put 200 instead of 220. So it's 220 squared plus 150 squared equals that. Take the square root of that. Alright, and then I'm going to invert it and multiply it by 220, which should be the same thing as taking 220 and dividing it by that. Alright, and then I'll multiply it by 10. And it's 8.26 volts. Any questions about that? 8.26 volts is the correct answer. The only difference between that and the lag circuit, when you compute voltage output on the lag circuit, it's X of C over the impedance. Alright, times voltage at the input. So in a lag circuit, we're trying to find the voltage across the capacitor. That's why X of C is the top on the numerator side of the fraction. And in a lead circuit, we take the output across the resistor, which is why R is on the top part of that fraction there. Any questions? So far, so good? All right. I think I'll end it there. Hopefully that makes sense to everybody.